Okay, so our traditional arc length formula for rectangular coordinates is our integral from a to b of the square root of 1 plus f prime squared dx. And like I was saying, it comes straight from the distance formula, and then you just take all these tiny little line segments and you sum together these infinitely short little line segments that come from this square root of 1 plus f prime squared from the beginning of your interval to the end of your interval. And then it's just like adding up a bunch of little rectangular pieces or adding up a bunch of little sectors of circles to find areas. Does the same kind of thing. Or adding up a bunch of little disks in their tiny little volumes to find volume. Same idea. We noted also that anytime your function has a discontinuity, or what else? What else causes a break that we have to, what else causes us to have to break up our integral? Yeah, cusp. Good. Discontinuity or a cusp means split the integral into multiple different integrals. And so if you know that the graph of your function has a cusp at x equals 2 or something, then you have to split it up at 2. Everybody good with that? Okay, cool. You guys are going to be very quiet again, huh? It's fun. All right. So what we also need to be able to do with arc length is we need to be able to find arc length using parametric functions, arc length using polar functions, and also even talk about arc length in terms of vectors. So the formula is going to be pretty similar. It's just going to come straight from the distance formula each and every time. So if we're talking about a parametric, we go from the first t value to the second t value, whatever t values we're interested in, and we use the small change in x squared plus the small change in y squared dt inside of a squared. So you can see clearly that that's just, straight up from the distance formula, right? It's change in x squared plus change in y squared square rooted, and we're just integrating it across whatever interval of t values that we need. So this is the arc length for a parametric curve, which you're going to want to know. Everybody good with that? Wonderful. All right, so let's take a look at this asteroid. And it's not an asteroid, it's just an asteroid. And let's see if we can find the length of it from 0 to 2 pi. So what's the first thing that we need to do? That's right, we need to find dx dt. Oh wait, nobody said that. Okay, what's dx dt? You guys know it's okay to unmute yourself and say things, right? Don't be shy. If you're wrong, I'll just tell you that you're wrong. So what's the derivative of our cosine cubed of t? It should be -3 cosine squared t times sine t, right? Using the chain rule. Derivative of cosine cubed is 3 cosine squared times the derivative of cosine, which is negative sine. And then what about dy dt? Should be 3 sine squared t times cosine t. Yeah? Should be good. And so we'll put this into an integral. And we should know something about this function. What do we know about this function? You guys know anything about this function? This function, our parametric function. Think about what's dy dx. Dy dx is 3 sine squared t, right? Cosine t over -3 cosine squared t sine t, which tells us that, you can hardly read that, I'm sure, but what does that tell us? It tells us that when t is 0, the derivative is indeterminate. And when t is pi over 2, the derivative is indeterminate. And when t is pi, the derivative is indeterminate. And when t is 3 pi over 2, the derivative is indeterminate. What does an indeterminate derivative usually show us? What do they usually tell us? That it's either got some kind of discontinuity if our original function is discontinuous there, or it's got a cusp, right? So it's either going to have a cusp or a hole, depending on our original function. If we look at our original function, we can plug each of those values in. So we'll say that there's most likely going to be a cusp at each of those values, which means that we can't just integrate from 0 to 2 pi. What will we need to do? Have to split it up. And this is a function that you should sort of get used to. Anytime you see that it's an asteroid, or if you see x equals, cosine cubed or y equals sine cubed or vice versa. I'll put this in so you can see what it looks like here on Desmos. What do we need? Cosine t, cosine t, because Desmos doesn't understand how to do powers of trig functions. Looks like this. It's got these cusps at 0, at pi over 2, at pi, and at 3 pi over 2. And just so long as the cosine cubed and the sine cubed don't have coefficients on them, each of these 4 pieces will be identical. So effectively, we could just do one piece of it and multiply it by 4. You note that if I put in like a 2 out in front of this, it's just going to increase the y values up to 2. Right? So in this case, they're still the same, right? We just have to note that they're a little bit different. Same thing if I put a 2 out in here, just so you have an idea of what these asteroids sort of look like, right? That's how they're manipulated. So that's something you should just sort of know. Yeah, Mahika, you're asking about the cusps. So these are definitely cusps here, right? You see the cusps at 0 and at pi over 2 and at pi and at 3 pi over 2. So we know that it's either got a discontinuity or a cusp there because, without looking at the graph, because the derivative is indeterminate at those values. Right? So that's, if sine is, or if t is 0, we have sine of 0 over sine of 0, which makes 0 over 0. Or if t is pi over 2, it's cosine of pi over 2, which is 0 over cosine squared of pi over 2, which is also 0. Same with pi for the sine, same with 3 pi over 2 for the cosines. Yeah. So what we'll probably want to do here is just do 4 times an integral from 0 to pi over 2 of this whole thing. And what should we do with this? We should square each of these derivatives. So if we're going to go 0 to pi over 2, that's just between 2 of the cusps, and we're just going to multiply it by 4 because we know what the graph looks like. So dx dt should just be 9 cosine to the 4th t sine squared t. And dy dt squared should be 9 sine to the 4th t cosine squared t. Everybody good there? Hopefully. what can I take out of this 9 cosine to the 4th in terms of a constant? 9 cosine to the 4th sine squared t equals 9 sine to the 4th t cosine squared t. I can take a 9 out of there, right? And when I take the 9 out of the square root, it becomes a 3. And if I multiply the 3 by the 4, I should have a 12 out here. And what else can be factored out of the cosine to the 4th sine squared?
Cosine squared, sine squared.
Right, and if I pull a cosine squared sine squared out of the square root, that should just be a cosine t sine t. And what's left here? I already took the 9, and I took a cosine squared and a sine squared, so I got a cosine squared. And I took the 9, I took a sine squared and a cosine squared. So cosine squared t plus sine squared t inside there. dt, which should give us 12 times the integral from 0 to pi over 2 of, well, just sine t cosine t dt, right? Cosine squared plus sine squared is 1, and the square of that is 1, so all that just cancels out. And now this is just a simple u substitution with u equal to sine. Du is cosine. This becomes 12 times an integral of u du. And now we change our limits. Sine of 0 is 0, and sine of pi over 2 is 1. So we just end up with 12 times u squared over 2 from 0 to 1, which is what? 12 times a half minus 0, or 6. So it's a total of 6 units long. Good or no? Cool. All right. Let's do another one. Let's see if we can find the length of one arch of the cycloid. And I'll show you a picture of what the cycloid looks like in a second. X equals 2 times t minus sine t, and y equals 2 times 1 minus cosine t. And we'll have to figure out what our intervals are here in a second. But before we do that, let's take a look at what's dx dt and what's dy dt. So what's dx dt? If I distribute the 2 through it, that's just 2. When I take the derivative of 2t, and the derivative of negative 2 sine t, that'd be minus 2 cosine t. What about the dy dt? Should just be 2 sine t. Everybody good with those? Hopefully. And dx dt squared ought to be 4, and then minus 8 cosine t. And then plus 4 cosine squared t, and then plus 4 sine squared t. Everybody agree with that? If we square dx dt and dy dt? Cool. All right. Then, what are our limits going to be? Are there any discontinuities on t minus sine t or 1 minus cosine t? No discontinuities, and we might have a cusp if we had a hole in our derivative dy dx, but 2 sine t and 2 minus 2 cosine t are never going to be equal at the same values. So what is the what is the length of our interval going to be? Since these are just t's within the arguments of the sine and cosine, we should be going from 0 to, to 2 pi. And if we were to graph this, just so you guys can take a look and see what it looks like, we've got what, 2t minus 2 sine t, and we've got 2 minus 2 cosine t. And if we go from 0 to 2 pi, it just looks like this little arch thing here. Nick, to answer your question, no, not necessarily. For example, if these were like 2 t's within here, one arch of this, one period of this would go from 0 to just pi. So real quick, if I put it at 4 pi, we get a second one. If I put it at 6 pi, we get a third one, and so on. If I threw in a, this one's, let's see. If I throw in a 2t there, 0 to pi gives me 1, and then 2 pi gives me a second one. So it just depends on what the argument of that sine and that cosine are, or what the period of each of those individual functions are. Does that make sense, Nick? Okay. All right. So how are we going to simplify down that radical expression right there? Yeah. We can pull out in fact, we'll pull out more than a 4 here in a second. Before we pull out anything, what about this 4 cosine squared t plus the 4 sine squared t? That's just 4, isn't it? So this becomes an integral from 0 to 2 pi of the square root of 8 minus 8 cosine t dt. And then instead of pulling out a 4, we can actually pull out a square root of 8, which is a 2 root 2. So we got an integral of 2 root 2 from 0 to 2 pi of just the square root of 1 minus cosine t. Good or no? And how will we integrate that? Gotta get a little creative for this one. Anybody? Nobody. Think about your half angle formulas. What's the sine of x over 2 equal? Doesn't it equal that? Yeah, which looks very similar to this. I just need a over the square root of 2 in here. So I could add that in. If I add in an over the square root of 2 here, what do I need to put out here? I need to put out another square root of 2, which makes this a 4. And then this becomes 4 times the integral from 0 to 2 pi of sine x over x sine t over 2 dt. Everybody see that? Good with that? Okay, so yeah, it looks like lots of people have lots of questions there. So to begin with, the 8 minus 8 cosine t came from, I don't know where my other colors are here for my tools. Give me some other colors here. Why does my toolbar show up? There we go. All right. So I don't remember who it was that asked, where did the 8 come from? Well, I had a 4 minus 8 cosine t. 4 cosine squared t plus 4 sine squared t is 4 times cosine squared t plus sine squared t, which is 4 times 1. So that's another 4 to combine with that 4 to make the 8. And then, so we recognize that this is a piece of the half angle for sine, which is why we added in this over 2 inside of it. Because if I had the over 2 inside of it, I could rewrite it as sine of t over 2, which is something that I can very easily deal with. And so we had out here a 2 root 2 originally, and I put in a square root 2 in the inside here, which means I got to put a square root 2 in the outside. This was in the denominator, so it's got to go in the numerator, and then the 2 square root 2 times the square root 2 becomes a 4. Does that answer everybody's questions on there? Shayla, Nick, somebody else who was asking, Mahika? Is that, you all good there now or no? Nick, you good? Yeah. All right, so now this is an easy integral, right? We got 4, and then we got the integral of sine of t over 2 should be negative 2 times the cosine of t over 2. And we'll integrate from 0 to 2 pi. Looks like that ought to give us negative 8 times cosine pi minus cosine 0. And that'd be negative 8 times cosine of pi is negative 1, and minus 1, which is negative 8 times negative 2, for an exact length of 16 units. Good or no? Any issues there? Any questions? Everyone okay? Okay. So we can also do this using polar coordinates. So for our polar coordinates, all we have to do is just turn our function r equals, f of theta into x's and y's. Remember that x is equal to r cosine theta. This out, it's been a while, and not x again. Y is equal to r sine theta. And so you just take your function, multiply by cosine theta, get your x, and then find dx d theta. Same with your y, multiply your r by sine theta, and take your derivative to get your dy d theta. So other than that, it's the exact same formula. Similarly to how we treated our derivatives in polar as parametrics, and we do the same thing with these integrals for arc length. That sound good to everybody? So we'll just do one of these real quick. We're going to find the length of the cardioid r equals 1 plus cosine theta. So I'll give you guys a second here. I want you guys to figure out the limits of integration, figure out the value for x and what dx d theta is, and the value for y and what dy d theta is. Sound good? All right, you got 2 minutes to find all those things. Ready, go. should have had x equals cosine theta, right? Plus cosine squared theta, if you distribute the cosine through. And y would be equal to sine theta plus sine theta cosine theta. Good there or no? And then you would have gotten dx d theta was equal to what? Negative sine theta, and then the derivative of the cosine squared would be minus 2 cosine theta sine theta. And our dy d theta would be cosine theta plus cosine squared theta minus sine squared theta. Or cosine theta plus cosine 2 theta if you preferred. Which, when we have to square, will probably make life a little bit easier. Could also rewrite this one as negative sine theta minus sine 2 theta if we wanted to. Make life a little easier there too. Everybody good with all that? Any questions there? Everybody good there? Y'all still awake? Okay. And just to remind ourselves briefly, what does the graph of r equals 1 plus cosine theta look like? We know it's a cardioid, which means it's got a cusp, right? And we'll note that it has that cusp right here. We start at 0 and come around here to pi, and it has a cusp there at pi. And so we'd want to, we should know what this graph looks like. So we should have known that already. But we'll want to break this up, and rather than trying to do 0 to 2 pi, having that cusp will give us an issue. So we're just going to want to do 0 to pi. We know it's symmetric across the polar axis there. So if we just do 0 to pi, we can double that. Make sense? So those are the limits you should have gotten. 0 to pi, square root of dx d theta squared. So that'd be sine squared theta. And then the negative and the negative is going to give you positive 2 sine theta sine 2 theta. And then plus sine squared 2 theta. And then plus cosine squared theta plus 2 cosine theta cosine 2 theta plus cosine squared 2 theta d theta. Good or no? And my handwriting isn't so great, but okay, I'm waiting. Let me know when I should stop waiting, Molly. Well, so first off, Molly, you know that 0 to 2 pi, yeah, you're supposed to have that graph memorized. Yeah, I mean, you know it should be 0 to 2 pi. It takes you one full time around it. But remember, we talked about all these polar graphs way back at the beginning of last school year, and we dealt with them a little bit also later on with the area stuff. So yeah, you should know what r equals 1 plus cosine theta looks like. It's cardioid. It's got its cusp. And the majority of it lies in quadrants 1 and 4 because it's positive cosine, right? And it's a cardioid because the a and the b values are both 1, right? 1 plus 1 cosine theta. So hopefully y'all remember what those graphs look like. Where that's a 2 theta at the very end. Is that what you're asking about? All right. We could try and simplify this down some and see if we get to a nice integral that we're going to be able to easily solve, but I don't think that we will. So let's just simplify it a little bit and see what happens. We got a sine squared and a cosine squared. That's going to equal 1. And we've got a sine squared 2 theta and a cosine squared 2 theta. That's going to equal 1. So we're going to have a 2 there. And so we'll have an integral of 2 plus this 2 sine theta sine 2 theta. And then plus this 2 cosine theta cosine 2 theta. D theta. And that's not looking real nice to evaluate by hand. So we'll just let our calculator figure that one out for us. It's possible to do, but unpleasant. So what does that come out to be on your calculator? And don't forget to multiply it by the 2 at the end there. Anybody? Eight. Wonderful. Sounds good. All right, I got 2 people that agree on 8. Cool. That should just come out to be a nice value of 8. Any questions or issues with that? Chances are they wouldn't ask you. I mean, I can't imagine they'd ask you to evaluate this integral by hand. Same with the previous one. I wouldn't be surprised if they wouldn't ask you to do that one either. Although the other one was easier than this one is. How would we do this one? Anybody know how you would do this one by hand? Very similar to the last one, but you have to. Yeah, you would, Nick, yes, you would take out the 2 first. And then this sine theta, sine 2 theta, cosine 2 theta. You have to use the sum and difference identities to turn those into just a singular trig function. And then you could use the same idea as before, but we don't need to worry about that. They won't ask you to do that. All right, cool. So that's polar. That's how you do it with polar. There's no real difference between that and the parametric, except you got to add in the, find the x and the y values instead of just having them given to you. Sure, Mahika, I can show the graph real quick again. There's the graph again. Remember, it's 1 plus cosine theta. So since A is 1 and B is 1 for 1 cosine theta, the ratio of A to B is 1, which means it's a cardioid, which means it has the cusp at the pole. And it means that if we add together the A and the B, that's how far we go into the quadrants where cosine is positive, so 2 units over here. The majority of it lies in the quadrants where cosine is positive because it's plus cosine, so that's quadrants 1 and 4. And yeah, that's how we knew it. That's what the graph looked like. Okay, back to it. So now we'll talk about vectors. So just briefly, I'm just going to do one problem with the vectors too. They're not too difficult. Got a particle moving along a path in the plane, right? So no longer just moving in the x, y direction, in just the x direction or just the y direction. It's not moving in a line, but moving in a plane. And we've got a velocity given by whatever the velocity vector is. Then we can find the displacement by integrating the velocity, each of the pieces of the velocity vector. And to find its position at some time later on from where we started, we just add that vector that we get when we integrate to the original position vector at the first value. That's, I think, pretty self-explanatory, right? You know, integrate the velocity to find a new position, and if you had an initial position, find the new position by adding your displacement from this integral of velocity to the original position vector that you had. We'll do that in a second. But you can also find the distance traveled, not just the displacement, but the actual distance traveled by using this same idea, integrating the x component of your velocity vector squared plus the y component of your velocity vector squared, all square rooted. So it's, once again, it's just the distance formula using your velocity, right? It's just the magnitude of the velocity vector being integrated, right? And that's the, the integral of the absolute value. So it's the integral of the magnitude gives you the total distance traveled for a vector. Everybody good with that? Okay, so let's do just the one here. We got a particle that is moving in the plane. It's got this as its velocity vector. And we know that its initial position at t equals 0 is the point 1, 5. So if we want to find the position of the particle at t equals 4, the first thing that we need to do is we need to integrate both the x component of the velocity vector and the y component of the velocity vector from 0 to 4. And that will give us the displacement from 0 to 4. So we'll do, I guess we'll do the x component first, 0 to 4. And the integral of 2 minus 3 pi cosine pi t dt should be what? T squared over 2. And then this should become minus 3 sine pi t using a simple u sub with u equal to pi t. Integrated from 0 to 4. And what does that give us? It gives us 8 minus sine of 4 pi, which is 0, minus 0 minus 0. Just gives us a displacement of 8 for the x component. And what about when we do the y? Should be an integral from 0 to 4 of the integral of 2t minus pi sine pi t dt. And that should be just t squared. And then it should become positive cosine pi t. 0. Which gives us 16 plus the cosine of 4 pi, which is 1. And then minus 0 plus another 1, which just gives us 16. And so our final position, if we started at 1, 5, ought to be 1 plus 16, comma 5 plus the 8. Oh, I did those backwards. Sorry, 1 plus the x displacement, 1 plus 8, and 5 plus the y displacement, which is 16. So we end up at 921. Good or no? Okay, but if we want the total distance, that should be the integral of the magnitude of the velocity vector from 0 to 4. So that should be 0 to 4, and the square root of what should be just t minus 3 pi cosine pi t squared. And we're not going to bother to even try to simplify this because it's going to become so unpleasant looking that we're definitely not going to be able to integrate that by hand. And we'll just approximate that using our calculator. So somebody let me know what we get. Okay, I'm waiting, Nick. What am I waiting for? Besides waiting for you to tell me what the value is there. Okay. Anybody got a value there? You got 33.53. So you rounded to 2 decimals instead of 3. That's a weird amount of decimals to round to. 33.53, 2 3s. Cool. Good or no? And if we wanted to determine the path the particle traveled going from 1, 5 to 9, 21, we'd have to find the position vector, the actual position vector. So we have this t squared plus cosine pi t as our y value, right? That's our y. And this one would be our x. And so when x was, should do this as a vector. When x was sine pi t. When when t was 0, x was 1. So if I plug in t equals 0 here, I get 0 for that. So I need to add 1 to it to get 1 just by using our initial condition there. And our y component would have been t squared plus cosine pi t. And when I plugged in 0 to that, I needed to get 5. So I'd have to add, this is 0 plus 1. So I'd have to add 4 to that. And that should be the actual position vector, just by using our initial condition. And with any luck, if you plug in 4 to those, you're still going to get 9 and 21 for your position. And so we could go in if we wanted to real quick. And look at this, giving us what? Now I've forgotten what we had. We had our x was t squared over 2, right? Minus, what was it, 3 sine pi t. What did I say, plus 1 for that one? And then what was our y component? It was t squared plus cosine pi t plus What do we have to add to that one? We had to add 4, is that right? And if we go from 0 to 4, should start us off at that 0.15 and finish us off at that point 921. And so that's the path that that particle takes. Everybody good with that? Any questions on that? Yeah, I'll go back to the other slide there, Delphine and Sheila. I added the 1 and I added the 4 just because when I integrated, I got t squared over 2 minus 3 sine pi t, but I knew that when I plugged in t equals 0, I needed to get an x value of 1. So if I plug in t equals 0, 0 minus 0 is already 0, so I got to add 1 to it to get that 1. And if I plug in 0 to the t squared plus cosine pi t, I get 0 plus 1, and I needed to get 5, so I got to add 4 to it. That's just the constant, from doing a basic differential equation. And we're going to do more of those, but once we do them proper. But does that make sense? Now? Okay, cool. Yeah, so, and now you can see why, even though it just goes from 1.5 to 921, it clearly is going a lot more units than what the straight line between those is. It goes 33.533 total units as it follows that curve along in the plane. Good?